Hi, thank you so much for watching. My name is Diego, and today we will review how to implement a physics-informed neural network in PyTorch. I uploaded the final code to my GitHub, and the link will be in the description of this video. Here, you will find some other examples that could be useful to you if you're just starting in this field. In this tutorial, we will solve the diffusion equation using a physics-informed neural network. As you can see, this is a time-dependent partial differential equation. We'll be giving the domain, the initial and boundary conditions, and also the exact solution. We'll be using the exact solution to evaluate our model and also to visualize the data. However, you will notice that we do not need to know the solution to solve this equation. One of the key concepts required to understand a physics-informed neural network is that a neural network is essentially a function. It's a function that has an extraordinary capability to approximate to any other function. That is why they have so many applications in so many fields. Our goal will be to train a neural network that approximates to the solution of a partial differential equation. A physics-informed neural network is nothing more than a neural network that follows the rules of a partial differential equation. But how do we make it follow the rules of a partial differential equation? Well, since a neural network is a function, we can obtain its derivatives. Then we can arrange them to follow the structure set by the partial differential equation. We'll call this arrangement F. Now, if a neural network approximates to the solution of our partial differential equation, well, then F should approximate to 0. And that is the condition that we will be using to train our neural network. We will evaluate our partial differential equation in a certain number of collocation points inside our domain. Then we will minimize this new loss function related to F. Usually, the training data is a set of points from which we know the answer, from which we know the outcome. And in our case, this data is our boundary and our initial conditions. So we will select NU points from our boundary and initial condition and use them to train our neural network, following the traditional mean square error that you may have seen it in another neural networks. Then the total loss will be the sum of the loss from the boundary conditions plus the loss from the partial differential equation. We will install the PyTorch. This is a library for design of experiments. Then we have to import PyTorch for training a neural network. We have to import matplotlib to plot the results, and NumPy to process terrain to see the data. And here, as mentioned, PyDo or PyDoe, we will use it for sampling, and the Latin hypercube, we will use that to select the collocation points. Okay, let's generate the data, and also let's visualize the solution to know what we are trying to approximate. To do that, I'm including these functions that will help us with the plots. Please feel free to pause the video, or remember that this code will be available in my GitHub. So let's just start defining a function for the real solution, which is right here. Let's call this freal. We'll take x and t, and we'll output a solution which will be e to the minus t times sine of pi x, and yeah, that would be. Now let's generate the data. So we have x, we have torch.namespace. We'll go from -1 to 1. Oh, let's make it 200 steps. And also t, which we torch namespace. Let's go from 0 to 1, and let's just say 100 steps would be your life. These values, the limits we're taking from the problem, you can see here. Okay, now let's generate a mesh. Remember that we're working in a two-dimensional space, so we need like a surface in order to obtain the result. So to do that, we use mesh grid, and it works something like this: torch that mesh grid. It says x and t. Now let's evaluate our function, which would be freal would be to freal of x and t, the matrix. And also let's plot the results. Plot 3D using the function we just created, x, t, and y real. Now let's see what we have here. Yeah, here we have the contour plot and the surface plot. So this is the function we will try to approximate. Since we will be working with a fully connected neural network, we cannot use the data we currently have without pre-processing it. Remember that when we use mesh grid, we obtained a matrix for each one of the input dimensions. Now, we will proceed with a column major flattening to obtain two vectors of 20,000 points each one. So, to do that, let's select it. Let's start with the testing group, as this we will use this one to evaluate our model. We will store both of them of the input variables. So as you can see, we'll have x dot transpose because we want a column major flattening. We're going to flattening. Yeah, and then we will add an additional dimension that we will use later for processing. We do the same here for the time. And we'll do the same for the answer. The only difference is that we are going to use the white real that we just created a few minutes ago. Also, let's set the lower bound and also the upper bound. The lower bound will be nothing more than x test, the first value, and the upper bound will be the last value. So let's set with -1. Okay, now let's print the shapes. That shape. This is only for visualization purposes. We cannot need to do that this last line of code actually. And also let's print the lower bound and the upper bound. We should be good to go. Yeah, you can see our X test store both vectors for space and time of 20,000 points each one, and the answer only has one column. Also, we have the maximum and minimum value for x, which comes from -1 to 1, and for time, that comes from 0 to 1. Remember that in a PINN, the training data is initial condition, the boundary conditions, and also the collocation points. So in initial conditions, when the time equals 0, then a y equals sign of pi x. And so it would be in the left edge here of this graph. So let's call that one left x equals. So we will save both time and space, so we will stack them horizontally. So it will be x. We want all the columns, all the rows, and only the first column. And yeah, and we want to add the additional dimension, and it would be none. We will do the same for the time. Yeah, we're good. Now let's call this left y, I'm sorry, it will be torch that sign of pi times of left x. But what left x? Only the x, not both x and time, right? So it would be only the first column, the first vector that it's here. So it would be all the rows, and only the first column. Yeah, we're good. Now we need to include another thing, which is this and squeeze. It's only to give it the right dimension. It's similar to what this none does. Actually, I think it does the same. Now let's go with the boundary conditions. In the boundary conditions, it tells us whenever x is -1 or x is 1, then y is 0. So it will be here, the top and also the bottom of this graph. So let's go and say bottom of x equals, it would be the same as we have here. The only difference will be that now we will be considering only the last row and all the columns, and the same for the time, last row and all the columns. And remember, this should be equal to 0, so let's call this bottom y equals to torch that zeros of y, bottom x, but shape 0, because we just want one dimension, and also how many do we want? Just one column out, right? So we get Let's see if we don't have an error here right so now. Oh, I'm sorry. Here it should have been something like that. Yeah, we're good. I'm sorry for that. Let's go here. And then let's go with the top. Here we have 0. We just want only their first column. And yeah, I think we're good to go. Yeah, good. Now remember that we don't use all the data. We just select certain points of the boundaries and the initial condition. So let's store them all of them in a single array. Let's call this x train equals storage that vertical stack of what we will save the left x, the bottom x, and the top x. Right, we're good. Now let's do the same for the y. So y train will be left y, bottom y, and top y. We're good. Whoa, we're not good. Oh, I'm sorry, it's the stack. Oh, yeah, I'm sorry for that. That's okay. Yeah, we're good. Now let's select just a certain number of points. Let's say that our NU will be equal to, I don't know, 100. Nothing that would be fine. We're just going to like 100 points from the boundary conditions. And let's see if that is okay. Yeah, I think it should be okay. Yeah, if it's not, then we can always go back. So now let's see. To do that, we select an index. And let's say random. Random, it's random. It's right here. Choice of x train. And we will select that shape 0 because that it tells us how many elements it has, how many points in U, and we don't want to replace them. Place equals false. Okay, so now the x train. I'm sorry for that. X train. Let's call this NU, which is the ones that we will use them to in one loss function. Will be our x train for index and all the columns. And for y train will be for the collocation points. Remember here we will be evaluating our PD. We'll be using the Latin hypercube sampling. That's why we needed that library by DOE. And we do something like this. So NF, x train NF will be our lower bound plus a range. So it will be upper bound like minus lower bound times this Latin hypercube space is like hypercube sampling, I'm sorry, and we want 2 columns and we want enough points. And how many points we want it? We should do it with 10,000 points. I think it should work well. Now let's go to the final step, which would be we also going to evaluate the PD in the points that we selected from our boundary condition. So that's what we're going to do here. So it's storage dot vertical stack what x string NF and also x string NU. Yeah, that should be good. Okay, the last part here is to send all our data to the device, which in our case would be a GPU, but it could also be a CPU. Okay, so that's also pretty easy. The only thing we need to do is x string NU equals x string NU float dot to device. Yeah, it should be the same for the NF, and it should be the same for the Y, and we use this to evaluate a function, remember. And the last part here that we need to define is it's a Y hat, and we'll call it F hat, I'm sorry. We'll call, and this will be torch that zeros of x train NF, of size x train NF, shape 0, remember the number of elements, and just 1 colon to device. Remember that f should approximate to 0 if it is working well. Okay, now that we have finished writing the code, we can see what it does. Python treats neural networks as classes, and from this special class called init module. First, we initialize our neural network. We set the activation function will be the hyperbolic tangent. Also, the loss function will be the mean squared error. With the reduction, we will try to reduce the mean. This module list helps us to change the architecture later if we want. We just input the Python array with the layers, with the structure we want, and the code does everything for us. We initialize our weights with behavior normalization, and we set the bias to 0. And then we start the forward pass, which means evaluating the function, which means passing through each layer and then activating it, except the last layer, because this is a regression neural network. Yeah, here we can see we also have here the boundary condition, the loss function for the boundary conditions. You can see you input the x boundary conditions and the y boundary conditions. The loss function, what it does is pass the boundary conditions through the neural network and compares it with the real value. There's the first loss, and also the loss of the partial differential equation. And here it's what makes this neural network a physics-informed neural network. First, we start by cloning our value to ensure that we won't mess up the data when we work with it, and also to activate its gradients. So as you can see, when we activate its gradients, we enable the differentiation, and that's what we were going to use. Okay, so we say f equals to forward g, so we pass the model. Then we take the first derivative using this long formula that I encourage you to review it. And then we take the second derivative. One thing to mention is that as we are inputting two variables, this variable will have also two variables in it. So to select the first derivative with respect to time, we will have to select the second value, and to select the second derivative with respect to x, we will have to select the first value. Then we evaluate f. F, remember, it's what we have here, is the first derivative of the neural network with respect to time minus the second derivative of the neural network with respect to the x squared plus this function that we have right here. And this is exactly what the input that we are setting here. This real value that you can see it here, it's only to give it the right dimension, but it's nothing out of this world. And then you can see that we compare the loss function against f hat. That should be 0, because if f should be close to 0 if the neural network it's close to the partial differential equation solution. So yeah, then the total loss will be the loss function from both the boundary conditions and also from the partial differential equation. Okay, now that we have written our neural network, we can start training. Let's start giving it some kind of architecture. So layers equals and an array of whatever we want. Let's say 2, 32, 64, and 1. The only conditions are that the first one should be 2 as we're the input to space and time, and that the last one is 1 as we're evaluating only y. However, we can change the number of layers and the neurons per layer. Here, pretty easy. Okay, now let's create a physics-informed neural network. We just call it this way, a fully connected network, as that how we define our class of layers. Now let's send our neural network to device. Yeah, we're good. Let's bring our neural network to see what we have. And yeah, you can see the activation function, the loss function, and the structure we just gave. Okay, now let's set the optimizer. So, which should be equals to, we'll use the Atom optimizer. However, we can try another one if we want. PyTorch.optim. It's a library that contains the optimizers. Atom. What we're going to optimize the PINN.parameters. Yeah, the learning rate. Let's set it to 1 to the minus 3, and now square to false. Yeah, and we're good. I'm sorry, this should be something like, yeah. Okay, now let's start training. Therefore, I in range, a certain number of steps, iteration, let's give it 20,000. You can give it more or less, depending what you want. Okay, now the loss will be PINN that loss of what? X boundary conditions, Y boundary conditions, and XPD. Remember that our boundary conditions were saved here in the extreme NU. So that's what we're going to include. Extreme NU. What else? We will save on our extreme Y train NU, which would be our Y boundary conditions, and also our XPD, which would be X train NF, or which will be our collocation points. Now let's set our optimizer to 0. So, grad, nice, into the back propagation. So loss dot backward, nice. Let's update the values with the optimizer. Yeah, we're good. Optimizer dot step, and then let's print the values. And to do that, optimizer, we will be using, yeah, we're good. And to do that, we'll be using the testing data, and it should be somewhere around here. Yeah, here's the testing data. The only thing we have to do it is to send it to our device too. That's what we're doing right now. And then we're ready to evaluate it. And let's see if, let's print it a certain amount of times. So let's do it 10 times. So this is a way of doing that, which would be 20,000 10. If the module of y against that it's equals to 0, then we will print. Here we will use with torch no grad. And this will use as we just want to report the value, but we don't want to create the gradients as this shouldn't influence in the training process. Okay, now the test loss should be equal to PINN dot loss, the boundary conditions, because that's the traditional way of computing it against the data we know. And of what? Of our X test and our Y test. And let's print the results, which would print what? The loss, which would be a training loss, and also the test loss, which would be, let's say here, training, and also testing, right? And let's save it something like that. Testing. Oh, let's give it a backslash. Okay, it should work now. Okay, the training, you can see, it will take a while, and I'll see you when it finishes training. Once we have trained our neural network, we can start visualizing the results. Here, we're using our physics-informed neural network to evaluate the whole dataset. And the code that you see right here, it's only to reconstructing matrices. Remember, this kind of neural network works with vectors, not with matrices. And here we are only reconstructing those matrices. These are the results from the physics-informed neural network. And these are the results from the real data. You can see that they are pretty close and pretty similar. However, if you want to improve the data, to improve the results, you can always modify the tuning parameters as the number of layers, the number of neurons, the learning rate, and you can change the optimizer and many other ways. And that would be all. Thank you so much for watching. It was my first tutorial, so I hope you like it.